All right, so welcome back to your next AP151 Heart Physiology Lab lecture. This lab lecture will be on reading an ECG and learning a little bit about the conducting system of the heart. For this lab module, you will need to complete the Cardio Lab worksheet, which it's its own separate file found in the module. You will also need to complete activities 2 to 5 of the PhysioX exercise 6 on cardiovascular physiology. Both of these you should submit by Wednesday, April 22nd, and like usual, there will be a quiz that I open up on Wednesday, April 22nd on this material at 8 a.m. So this is the heart's conducting system. The heart exhibits autorhythmicity, which is the ability to initiate its own heartbeat. This is really important for the heart to be able to do, and the conducting system is really interesting to see. The conducting system sends electrical impulses that start and propagate these electrical impulses to all of the contractile cardiac cells. So the cells involved in muscle contraction that contract the heart are started within the heart itself. This conducting system starts in the sinoatrial node, which is located in the upper right atrium, and that's seen by that little yellow circle there. From there, the impulses travel to the atrioventricular node, which is found at the base of the right atrium. From there, the impulse travels down the interventricular septum in the bundle of His, into the right and left bundle branches, and then eventually into Purkinje fibers, which take this electrical signal to all the contractile cells of the myocardium. Specifically, it's taking cells to cardiac cells that are connected with gap junctions, and they're connected by intercalated discs, which you've probably heard of before, and they just allow this electrical signal to pass consistently and simultaneously through all the cardiac cells so the heart can contract at the same time, or the chambers that need to will be contracting at the same time. So the electrical impulse of the heart's conducting system starts in your SA node. The impulse then travels to your AV node in the floor of the right atrium. From here, from the AV node, the impulse is slightly delayed, and that allows for the ventricles to completely fill with blood. If the impulse traveled directly into the ventricles right away, the ventricles wouldn't fill completely with blood, so your ventricles would be ejecting half-full chambers of blood, which wouldn't be useful. So at the AV node, the heart signal is slightly delayed, and we are able to see that on an ECG, an electrocardiogram, where that delay occurs. From the AV node, the impulse enters the AV bundle of His, which extends into your interventricular septum, which divides your ventricles. And once within the septum, the AV bundle divides into left and right bundle branches. And these bundle branches pass the impulse to the Purkinje fibers that begin at the heart apex. These Purkinje fibers that begin at the heart apex will eventually extend superiorly from the apex to all of the cardiac cells in the ventricular myocardium. And the myocardium, again, are the cardiac muscle cells that will cause muscle contraction of the ventricles. So this takes you through the first two steps of the heart's conducting system. You can see how the impulse starts in your SA node, travels to your AV node in step 1, and then in step 2, the impulse is traveling into the atrioventricular bundle of His in the septum. Here's steps 3, 4, and 5. You can see the impulse now starting to travel down the septum. It's shown as like a greenish highlighted color into the bundle branches in step 4, and then up through all the cardiac muscle cells by the Purkinje fibers in step 5. So you're seeing kind of how this electrical signal overtakes all the muscle cells eventually, and that's what gives the heart its autorhythmicity. It can establish its own heartbeat because the electrical signals that start in the SA node eventually travel to all of the cardiac myocytes, which will cause ventricular contraction. So this idea of an electrical signal being passed throughout the heart can be measured with an ECG, which I mentioned before, an electrocardiogram. This is showing one kind of cycle of that ECG. And we're going to go through each part of an ECG here, and I'm going to explain what each kind of divot or increase in the graph refers to. This is showing voltage over time, and the P wave, which will always be that first wave shown there, that results in response to SA node triggering the first part of this conducting system. So when the SA node starts the conduction system of the heart, it causes depolarization of the atria. And depolarization just means that this impulse has been started to pass through the atria. And it's shown by this P wave on the graph. The PR interval is the little space in this line between the P wave and the QRS complex, which is the really big upswing in the graph. That PR interval is that delay we talked about of the AV node. So this is where the impulse is delayed to allow your ventricles to completely filled with blood, because again, we don't want your ventricles ejecting half full chambers. After the impulse travels from the AV node, it'll go into your ventricles, and the depolarization of the ventricles refers to the impulse traveling through the ventricles, down the bundle of His, into the Purkinje fibers. And this QRS complex refers to complete depolarization of the ventricles. It triggers the main pumping contractions of the heart. So this is where your ventricles, right after this, will contract and eject the blood into your pulmonary trunk or your aorta. Then we have an ST segment, which is again a flat part of the graph. It should be flat in a normal heart. Beginning of ventricular repolarization, which means this is when the ventricles go back to normal or baseline, so back to relaxing, filling with blood. And then the T wave stands for ventricular repolarization. So this is kind of one conductive system of the heart, starting from SA node triggering, showing how that impulse travels through the atria, causing depolarization in the P wave. Then the impulse travels through the QRS complex, causing ventricular depolarization. And then the T wave, ventricular repolarization, meaning the ventricles are then going back to normal. When they hook you up to this in a hospital, they get a complete read of ECGs in a row. So they measure your cardiac conductive cycle over and over again. So they'll measure the distance between your P and QRS complex and your QRS complex to your T wave to make sure that your conductive system in your heart is functioning correctly. This is extremely important to help determine and diagnose diseases, because if something's wrong with your heart, if your heart has a murmur, which is a filling up of a chamber in an opposite direction, or if something else is off in this conductive system, it can show if someone's having a heart attack, if someone's heart is beating too fast or too slow. So this is a very important diagnostic useful tool. If you're interested, you can go and get certified in reading ECGs and get a pretty great job reading ECGs all day. So anyway, just a review of what all these stand for. If we look at just two kind of cycles of this, the P wave will be your first little hump. The QRS complex will be the sharp upswing, kind of triangular shaped. And then the T wave is the final repolarization step of the ECG. And again, you'll see above how it keeps going over and over again. Each little square between measurements can be measured, and you can measure the time in seconds between each portion of an ECG, and that can help to diagnose disease or anything else that could be going wrong. These are the 5 phases of the cardiac cycle. The cardiac cycle ties in everything that happens within a single heartbeat. So not just electrical signaling that goes through, which is what we're focusing on, but also ventricular and atrial filling, ejection, and how the valves open and close. So that's what I mean when I say cardiac cycle. In your worksheet that you'll have to submit, they ask you to measure the PR interval and the QT interval. This is really simple to do. You first need to know that each box in an ECG graph represents 0.04 seconds. So you will count the boxes between the beginning of the P wave and the beginning, or wherever that upswing of the R is in the QRS complex. That's the PR interval. And there's about, in this example, about 4 squares or 4 millimeters, which represents the PR interval. So those 4 boxes, if each box is 0.04 seconds, you just take 4 boxes, which is the length from the P wave to the R wave. You take 4 boxes times 0.04 seconds per box, and you get 0.16 seconds for this PR interval. And that's normal. The normal PR interval is less than 0.2 seconds, so that is normal. It'll also ask you to calculate the QT interval. And again, for QT interval, if you can see here, you go from the start of the Q wave, which is the top peak on the, it's the start of the QRS complex, and you'll go to the end of the T wave. So you can see there that measures about 9 small squares. So you take 9 and you multiply it 0.04 seconds per box or per square, and you get 0.36 seconds. So that's how you measure the QT interval. So you will need to know how to do that for your worksheet. You will also be asked to determine the heart rate from the ECG example that you're given, and you should show the calculations. The directions to do this are included in your worksheet, but I just wanted to talk through them. A single cardiac cycle is from the start of one P wave to the start of the next P wave. So you can count the number of small boxes for a single cardiac cycle from the start of one P wave to the next. And if the P wave is difficult for you to see, you can count from R to R, which is the QRS complex. The Q is the first downward divot, and the R is the top pointed part of that. You can multiply then the number of boxes by 0.04 seconds per box to give you seconds of a total cardiac cycle. So this will give you the time for one cardiac cycle. Once you know the time for one cardiac cycle, that's what X should be in this equation. So X is the average length of the cardiac cycle in this example that you'll be looking at. And again, they're going to give you an ECG to read. To determine heart rate, all you do is you take basically what you got, and you know that there's 60 seconds in 1 minute, and 1 beat stands for 1 cardiac cycle. So 1 beat of the heart would be 1 cardiac cycle. So 1 beat would be over X, which is the value of in seconds of that average length of the cardiac cycle that you found, again, by just counting the number of squares from P wave to P wave or from R peak to R peak. So you'll basically take just the 60 seconds divided